So, how you guys feeling? Like on Monday, my main goal today is to address any questions you guys have, either about the test itself or working on the practice test, or even homework questions are a great thing we can spend time on this week. So what's on your minds?
Can we go through C on number 4?
Yes.
On the practice test? The last part of the math.
Yes, and I will admit, there's kind of two mistakes that I made floating around here. One is, depending on which when you access the practice test, this question doesn't have a mass in it, and you kind of need one. So I wrote on my answer key, assuming mass is 25 kilograms, and then I updated the original file, but depending on when you accessed it, you might not have that. You may assume the mass of the sled is 25 kilograms. The other mistake I made is that when I was making my answer key, I just forgot to write down how to find normal force. I must have been distracted by something, and then when I turned back to my work, I just thought, oh, it's done, I'm moving on. That's not true. The problem here is there's 4 forces to solve for, excuse me. And I showed about how to find 3/4 of them. The first force was already given, 100 newtons. And if I ask you for magnitude, that's all the information you really need to give. I just added the last piece to make sure it was clear that these components are the components of the 100 newtons, just broken up into X and Y axes. And those components are what make it into the axes analyses to follow. Force of gravity has its own formula, and that calculation is down here. Force of friction, to find that, I actually, since we don't have a mu to find force of friction, I instead looked at net force in the x-axis, considering that the net force across the entire board is 0 if the object is moving at constant velocity, which was the answer to the first part. All the forces present must add up to 0, and there are only 2 forces within the x-axis, the x component of the rope pulling forwards and friction pulling backwards. There would have to be some friction, because if you are pulling forwards but you are not accelerating, there is something resisting you, and most often the thing that is resisting motion is friction. And in this case, if those are the only 2 x forces and they add up to 0, they must be equal and opposite. So friction is equal to negative 70.7 to equal out with the positive 70.7 newtons pulling forwards. The last one here is normal force, and in this specific case, normal force is opposite but is not equal to gravity, because there is a total of 3 vertical forces that must add up to 0. Normal up, gravity down, and the y component of the rope tension also up. And what's happening here is the rope is basically reducing the effort that the ground has to undergo in order to keep the sled from falling through it. So the rope pulling upwards means the ground doesn't have to push as hard, and that has driven down the overall normal force, as opposed to if the rope was only pulling straight sideways and there was only 2 vertical forces that would need to cancel out. In that case, the normal force and gravity would probably be equal and opposite, but here it doesn't quite work out that way. This is a similar scenario to if you are standing on a bathroom scale and you use a counter to partially lift yourself up and the number on the scale decreases. It's not because your weight changed, because the scale doesn't know how many atoms are inside your body. It's just that the normal force requirement of the scale dropped because you are reducing the effort the scale has to use, using your arms by lifting yourself upwards partially. So it's the same thing here. The upward component of the rope is making normal force's job easier, and that's why it's not exactly equal to gravity. And I apologize for this work not being on my answer key. Does that address your concerns? Okay. Okay.
Can we go over the tension problem? I wasn't here on Monday, I don't know if you guys did, but the flower pot.
Yeah.
Just like that.
Any other questions about this one before moving on? All right. Flower pot. So, this one is technically very similar to one of the ones we did in lecture, where we had all the ropes pulling in different directions and all the tensions have to add up to 0 to hold something in place. Main difference here is just that the two ropes are equal but opposite angled. They're just mirrors of one another. And this would imply that their X components are working against one another, but their Y components are working together to overcome the weight of the flower pot. So it is, I would still consider this vector addition. There's two vectors that, well, there's technically three vectors that are adding up here. The weight of the pot down, and then the two tensions up and out. And all of these forces have to add up to 0 because the goal of this assembly is to hold the pot in place. If you want something to hold still, the net force on it needs to be 0. So two main assumptions at the start. Net force is 0, and that's true in both axes. So in my math to follow, net force in the x-axis is 0, net force in the y-axis is 0, no matter how many forces are in each axis. Next assumption is that since the tensions are on angles, they need to be divided up into their components. Now, we don't have numbers for tension, meaning that we can't get numbers for the components, but we can still do the trig for them and determine a trig statement for the components. Because what I've got right here, net force x-axis is equal to 0. It has to be for the pot to remain in place. And the only two x forces here are the x components of the two tensions, seen here and here. They must be equal and opposite. They must be canceling out, but we don't have numbers for either or. These are two separate unknowns right now. And then down here, this is the y-axis analysis. Here you've got the two y components of tensions pointing up and gravity of the weight of the flower pot pulling down. And we can find the weight of the flower pot. I don't really consider that to be an unknown. Problem is though, we don't have the y components either, so those are two more unknowns. So as these are initially written, that's two equations, 4 unknowns, which is not workable. So all this trig over here is to try to take those components and rewrite them in terms of the unknown tensions. The goal being, instead of T1y, T2y, T1x, T2x, it's just T1 and T2 in multiple places. So, starting from this rope, if that's 60 degrees, then sine of 60 would be the y leg over the unknown tension. Therefore, the y leg would be unknown tension times sine of 60. And we can write that in place of T1y, the goal being to reduce the number of unknowns, make it just T1 and just T2, rather than a bunch of components that are unique a bunch of separate components with their own names. So all this work over here is just to turn the components, the legs, into something that references instead the overall tension. And sine 60 and cosine 60 are used repeatedly, and you can just find a number for that. You don't have to leave it in that form. As long as you know the angle, you can just pop it into your calculator and get a number here. I just left it as the sine or cosine for the time being. But that means that each of the legs is now a function in terms of the tensions that we're after. And if we plug those into our equations instead, that's going to reduce the number of unknowns. And that would eventually allow us to do a 2 equations, 2 unknowns type thing. Now in the x-axis, this one actually simplifies pretty nicely because this is our original statement. The 2 x components must be adding up to 0. I then plugged in the 2 trig functions from over here. So t1x is t1 cosine 60, t2x is t2 cosine 60. Put those in instead. That said, they point opposite each other, so one of them has to be negative. Doesn't really matter which, as long as one of them is. And usually the goal with 2 equations, 2 unknowns is to take this and solve it for one of the unknowns to plug into the other. So the goal would be to end up at a statement of t1 equals or t2 equals. But an interesting thing kind of happens when you take this statement to do that. What I did is I took the negative term and just sent it over to the other side, giving t2 cos 60 equals t1 cos 60. And normally if the angles were different, we could like solve for t2 by sending this cosine over and you get a weird looking fraction. But in this case, the angles match, and dividing both sides by cos 60 just kind of cancels it out and tells us that whatever the tensions are, they're the same. So this is still technically 2 equations, 2 unknowns, it's just the 2 unknowns are identical. And we can use that, I used that down here, rather than labeling it T1 or T2 anymore. These are still the Y components, because we've got the sine 60s here. But since it's the same tension twice, I just stopped labeling them. I just made it T and T instead of T1 and T2. Which would be the same effect as if I kept in the T1 and T2 and then just substituted one in for the other. So this is 2 equations, 2 unknowns. You should take whatever you get for T2 and plug it in down here. But since they're equal, it kind of stops mattering which one's which. From there, these 2 point up and are working against the weight down. So this is the mass of the flower pot times negative 9.8. That just becomes negative 98. Send that to the other side. Then this would add up to 2 times t times sine 60. Divide both sides by 2, divide both sides by sine 60. And that tells me eventually that both tensions are 56.6. And they're the same basically just because they're mirrors of each other. If the angles match in a situation like this, the tension magnitudes would be the same. And that only worked out because the angles match. If the angles were different, it would get, oh, we did an example in class where the angles were different. Does that help, or would you like me to?
No, that's good.
Okay. I guess we don't. It's all right if there's no specific questions on your mind right this second. What we can do is I can just stay in here with you guys if you just want to keep studying, and if any questions pop up while you're doing that. It's also a good time to ask about homework if you've been working or struggling on anything there. if there's nothing immediately on your minds right now, we can either pause here, I'll just wait until you guys have questions. Or we could call it for the day if you'd rather study on your own. Or alternatively, I can just ramble about science for another half hour. It's kind of whatever your preference is.
I might have a homework question.
Yeah, you guys just want to kind of work on your homework in the room with me, that's fine. That's also fair. Again, this is review week. The whole point is to make sure you get what you need, even if everyone needs different things. I'll go ahead and cut the camera so it's not a bunch of dead air.